we were looking at the LP operator norm. Of the Beurling transform, the final thing we had to do was to show it's LP bounded for p bigger than 2 and get an estimate on the actual LP norm, on the operator norm, and show that it goes towards 1 as p tends towards 2. So this is what we did. So we defined this strange operator, or strange looking operator, Tf of zeta to be 1 over 2 pi, integral in the principal value sense of f of zeta plus z mod z zeta dz, right? And using the fact that we have the Hilbert transform, the one-dimensional Hilbert transform was bounded in LP, we could show that this thing was bounded in LP, which was kind of a lengthy computation, but we did it. Is bounded in LP, but we lost control using Hilbert transform. It basically came down to using Courier formula and then breaking this integral up on lines, and on each line, after some changing of things around, it turned into the Hilbert transform. Okay, and that was useful, so because it turns out that if we compose twice with this operator with some function, it is minus the Beurling transform of this function. So that instantly gives it the Beurling transform is bounded in LP. So because take f in LP, that's the same as taking t star of f, which again is an LP, and then take t star of that thing, which again is an LP, and the bound will be controlled. So all of that stuff is fine. So S is bounded in LP, or bounded as an operator. I'm going to say op dot for operator now. Yeah, and all we need is a control on the actual operator norm, and so this is where the control comes from. So let CP denote operator norm, op norm, denote LP, op norm of S. Then there is a theorem, and it comes with some names. Riesz Thorin convexity theorem. That says that C, well, let's say it this way, CP is a convex function of 1 over P. So what that means is that if we plot a graph where on this axis we have 1 over P, and above we put what CP is, then that thing will form a convex function. Yeah? And there's one value of CP that we know, which is when P equals 2, because when P equals 2, we saw that this thing is actually an isometry in L2. So it's actually got a, when P equals 2, it has a bound of 1. So if we put a half here, that corresponds to P is 2, And in that case, we know that this graph is exactly equal to 1, right? And it's a convex function. So whatever it's doing, maybe it's doing this, or maybe it's doing like this, or whatever. We don't actually care anymore because it's a convex function and therefore it's a continuous function. Yeah? So as p approaches 2, 1 over p approaches 1 over 2, and therefore Cp approaches the value 1 just from this. Do you all see that? Are you all happy? Yeah? So this is the value of Cp going up like this. Yeah? So this theorem gives us what we need, along with the fact that we know that C2 is equal to 1. Yeah? And this theorem again is something we're going to skip. It's a classic theorem. It's in alphas. So to completely nail this stuff down, to have no gaps, you'll have to also read the proof of this theorem. But we will just leave it. All right. Everybody happy? Yeah. So with these gaps, with these things still to be read or fully understood, that does it. That completes the proof of Stoilov decomposition, right? And that's quite a journey, right? So the actual statement itself is very neat. It's very elegant. It's very easy to understand. You could explain it to a first-year graduate student. You could explain what quasi-regular mappings are. You could explain everything about this to the statement to a first-year graduate student, yeah, or even an advanced undergraduate. But to actually prove it, we had this quite long journey, right? We had to define these various kinds of operators. We had to prove various identities about what happens when we differentiate them. We had to find this relationship that the Beurling transform takes the anti-conformal to the conformal part of the matrix. And then we had to work to show that these things are bounded in LP and then try and control their norms. So initially, it doesn't look like single integrals have anything to do with the question. Right? The question is about mappings from R2 to R2 whose gradient belongs to a certain subset of matrices that don't send balls to ellipses that have axes which are axis ratios that are too long and thin. But the actual tools turn out to involve studying something quite different. And that's one of the things, I think I've said this before, one of the things that's appealing about this, and one of the reasons that this is something I wanted to show you, that to answer questions about natural questions about elementary mathematical objects, sometimes you have to go in a certain direction and develop theory that seems quite unrelated to the initial objects of study. But these are the key objects of study. So the guys working in quasi-regular mappings now are principally studying single integral operators and various properties of single integral operators which are related to these questions, and proving very sharp, very delicate theorems about them. And that's simply what's necessary to understand these questions further. There is a conjecture about the optimal operator norm, and I should have written it down, but I think the conjecture is when p is bigger than 2, the operator norm should be p minus 1. And that's a long open conjecture. Many smart people worked on this, tried to get it a bit closer. Many methods involved, methods from probability. This is a very famous question. And so anyway, this is an important question and still open. And if you want to think about it, give it a go. The big prize for actually answering this. All right, so that will complete our work, our development of this subject in R2. Okay, everything we've done is in R2, and there's a reason we have these strong methods from complex analysis. These single integral bounds are much easier to prove in 2 dimensions for that reason. The whole theory does exist in Rn, however, but it's harder. It's technically harder. But it's also strangely, the theorems are more restrictive. There's more restrictions on being a quasi-regular mapping in R3 and above than there is in being in R2. So it actually has also quite a different flavor. Nevertheless, what I'm going to do now is I'm going to sort of summarize briefly the main points about quasi-regular mappings and Rn, and the main differences. And we're not going to prove any of these theorems. We're just going to state them. But they are analogous theorems to the ones we've been studying. Okay, so this is the next topic. Okay, so let F be some mapping for some region omega contained within Rn into Rn, and the definition is the same. So if we take the operator norm of the function, power n, it should be bounded by some constant k, the determinant of the derivative. And the picture is the same, so I can try and do this in 3 dimensions. So if this is the shape of the image of the solid 3-dimensional ball with the gradient of the mapping f at some point x, imagine it forms some kind of an ellipse type shape like this. Then what is the operator norm? It's the longest side of this ellipse. So let's imagine taking the smallest radius of 3-dimensional ball that contains this ellipse type shape. So this is our 3-dimensional ball, right? Then this thing here is the operator norm, this radius, right? So the operator norm, this is in 3 dimensions, the operator norm to the power, n, or the power 3 in 3 dimensions, is the volume of this 3-dimensional ball. And what we ask for is that the volume of this 3-dimensional ball isn't too much bigger than the volume of the actual image of the unit ball under the gradient. In other words, this ellipse type shape here. Yeah? So that constrains the shape of this ellipsoid type thing to not be too long and thin. Because if it was too long and thin, then the volume of this thing would be so much smaller than the volume of the smallest solid ball containing it. Yeah? So it's exactly the same as in, it's exactly the same picture as in 2 dimensions, but in 2 dimensions we can just talk about, the axes like this, where it's harder to do that in 3 dimensions. But the moral is the same. We're talking about gradients that don't deform the ball into things that are too long and thin compared to the actual ball. If we had k was equal to 1, then there would be no. Then it would not be the case that the ball containing the ellipse has got bigger volume than the actual ellipsoid type thing, and therefore the ellipsoid type thing would have to be a ball. Yeah? All right, everybody, this stuff we've talked about before, but hopefully you're all clear about it. Thumbs up if that all makes sense to you in higher dimensions. Cool, all right, so same definition, same intuition. This is the kind of mappings we are considering. And the main theorem one of the main consequences we got from Stoydov decomposition was that these mappings are open and discrete, and that's still true in higher dimensions, and that's a theorem by Riesz Thorin. Let me try and spell Riesz Thorin. He might still be alive even. If so, he must be very old. Okay, so quasi-regular mappings are open and discrete. So open means that the image of an open subset of omega is going to be open. Discrete means that if you take the inverse of any point in the image, there will be at most countably many pre-images, and the cluster points will be outside, will be on the edge of the domain. It won't be inside the domain. Yeah. This, I think, was proved in I would say 60s or the 70s, not that long ago. Well, maybe for you that seems like a long time ago. But yeah, relatively recently. Yeah, and we have this for free as a very mild consequence of the story of decomposition, because, just recap that, in 2 dimensions, if we have a quasi-regular mapping from some region omega to whatever, so this is our quasi-regular mapping F, we construct some mapping G that has the same Beltrami coefficient as F, and let's call that thing G, to map to some other domain, and then some holomorphic mapping like this from this guy onto like this. So we go from this to this, right? So we're going to have F is phi composed with G like this, right? And so all that stuff is for free. So G is quasi-conformal, it's invertible, it's continuous. So G is a homeomorphism. Let's finish that word. And phi is holomorphic. So the fact it's open and discrete just follows very easily, right? We pull back any point here, it's at most countably many points here with cluster points on the edge. The homeomorphism pulls it back to the same property. Yeah? So that is one of the principal theorems. But we have other theorems that are true in dimensions 3 and above that are not true for quasi-regular mappings in dimension 2. And that comes down to the difference between conformal mappings in dimensions 3 and above. Not comes down to, but it's related to the difference between conformal mappings in dimensions 3 and above and conformal mappings in dimensions 2. So let me erase the board, and we will talk about this. Okay, so as we talked about, the radical difference between conformal mappings in 2 dimensions and in higher dimensions is that there's a whole function class of conformal mappings in 2 dimensions. There's a whole theory of these functions, holomorphic functions. And in dimensions 3 and above, there's just one example, essentially, after transformation, or maybe you consider it 2, but one non-trivial example, which is down to Liouville's theorem. Which, once again, is that if we have F, and let's take it to be C3 from omega into Rn, and then it's conformal, so the gradient of X belongs to the conformal matrices everywhere. Then there exists some A belonging to Rn, a conformal matrix M belonging to conformal matrices, some, let's call it constant C belonging to Rn, such that f of, that's right, x is equal to x minus a over mod x minus a squared. This reflection, which I'll write in a second, times this Mobius mapping like this, put brackets around these, and then plus constant c like this, where I is just a reflection through the first variable. Right, so we talked about this before. This is obviously extremely restrictive. That means that it's either an affine mapping or it's this thing which is inverting through the surface of the sphere that reverses orientation, so we need something to flip orientation back This is the reflection through one coordinate, and then we can just compose on the left by any conformal mapping. Morally, that's the same as just turning this reflection plane around in a different place. And that is the only example of a non-trivial mapping. Now, we proved at the very start of this course, Riemann mapping theorem, that if we have any simply connected open set, we can find a bi-holomorphism between that simply connected open set and the actual disk, right? This is the first theorem of this course. Let's consider the analog, or the attempted analog for this. If we have a ball, what do you think the image of the ball can be under a conformal mapping in dimensions 3 and above? And a ball, we can just might as well take the unit ball. What do you think the image of this thing can possibly be under a conformal mapping in dimensions 3 and above? Okay. Well, if there was no I part, if there was no this part, x minus a over x minus a squared, then for sure it would just be a ball, because that would just be an affine mapping, right? An affine mapping whose gradient is in conformal matrices. Yeah, so the issue is, what is this thing, this reflection from the surface of the ball, actually going to do? So let's check it out. So if we have such an f, then we know that the reflection will just not change whatever shape we have. This part will not change whatever shape we have, again, because its gradient is, this is inside the conformal matrix, so it's just lambda times the rotation. It will just dilate and rotate things around. So if it's a ball, it will still retain a ball. Well, it would just be, all these things move it to similar shapes. This is just a constant. So the actual action we have to consider is this a x minus a over x minus a part, or x minus a squared part. And we'll see what can happen to a ball under that. Yeah? So if we have if we are looking for something which is a diffeomorphism, then we don't have the a inside the ball, because if we have the a inside the ball, then we have a singularity and it's just no longer continuous. So I should ask this question about, given a ball, the if f restricted to the ball forms a diffeomorphism. And if it's a diffeomorphism, then obviously the inverse is also going to be conformal just by calculus, or multivariable calculus. So let's consider action of x goes to x minus a over x minus a squared if a is not inside the ball. Okay, so by rotations, we can assume that if a is not inside the ball, then a is just going straight up in the direction of the E3 coordinate. So take a to be equal to, say, alpha E3. So let's do this in 3 dimensions. So okay, so then let's consider what we have. So then for any x inside the unit ball, let's call this thing something specific. So let's call this, say, q. Then what is q of x? So this is the a we've assumed we have. So we're going to have x1, x2, And here we're going to have x3 minus alpha, and then that's going to be over x1, let's write it like this, that's going to be over x1 squared plus x2 squared plus x3 minus alpha squared. Yeah? Just putting this directly into this. Yeah? And then notice that this thing is invariant under rotations of the x1 and x2, rotations of the plane, right? So G of the image of the unit ball does not notice rotations, or not, let me say this, is invariant under rotations. I should not say does not notice. In the sense that it remains the same set. Let's call this rotation r of theta, where we rotate the first two coordinates. So cos theta minus sine theta, cos theta, and this is 0, 0, 0, 0, 1, right? So all this thing does is it takes x1 and x2 and it rotates them around, right? So this is our three-dimensional space. It's rotating around the plane and leaving the E3 coordinate invariant, yeah? So if we have any point inside this ball, right, it's of this form like this for some x. If we rotate around, it's just going to change the x1 and the x2, right? But that new x1 and x2 will still be a point inside the unit ball. So the image of this guy is completely invariant under this rotation, right? The set itself doesn't notice it. Are you all with me here? Yeah, thumbs up if so. Cool. So imagine this thing is here above the xy plane. We know that if we rotate it around, it doesn't change. So if we just take a slice through it, just one slice through it, then we'll understand it completely, because the rest of it is just that slice rotated around. Yeah? So enough to consider. Slice by, let's take the xz plane. Which is a set of x1. So I'm swapping between x1, x2, x3, and xy, z, but I hope that's okay. So x1, 0, x3 for any x1 and x3. Right? So if we consider the slice through this plane and understand that slice of our set G of B1, then we'll know everything. Yeah? So if we consider G of image of the unit ball intersected with this plane, well, what's that? So that means that we have that the x2 coordinate will be 0, right? So this is the image of G of x for any x in the unit ball. The x2 coordinate is here divided by this constant here, right? But if the x2 coordinate is 0, yeah, then it just becomes 0 in this expression. Yeah? So then this thing will be the set of things of the form x1, 0, x3 minus alpha over x1 squared plus x3 minus alpha squared, for x1, x3 belong to R. Oh, no. For x1, x3 is absolute belonging to the unit ball, I should say. So let's express that like this: x1, x3 such that x1 squared plus x3 squared is less than or equal to 1. That's our slice. Yeah? Cool. Now, let's let's create a function in the complex plane. Let's define, so lots of functions here. Oops, no, let's start with an f and define. So define w of x1 plus I x3 to be x1 plus I of x3 minus alpha over x1 squared plus x3 minus alpha squared. Is this mapping looking familiar to you people? Let me write it like this. So this is the same as x1 plus I x3 minus alpha times x1 plus I x3 minus alpha complex conjugate, right? Yeah? So then this thing, what is it? Where have we seen this kind of stuff before? Or why not, maybe not we, where have you seen that kind of stuff before? So it's the same as the complex conjugate as 1 over x1 plus I x3 minus alpha. Yeah? What kind of mapping is that? So ignore the complex conjugate for the time being. Just look at the thing without the complex conjugate. Where have you seen that kind of thing before? What kind of mapping is it? Come on guys, some of you complex analysis with me. What kind of mapping is that?
Mobius map.
It's a Mobius map, right? It's just a Mobius map. Yeah? It's just a mapping with a form AX or AZ plus B over CZ plus D, right? And in this case, on the top we just have a constant, on the bottom we just have the complex number minus another complex number, yeah? You will see that this is a Mobius mapping. Thumbs up if so. Sanka, do you see this as Mobius or not yet? You okay? Good. So this thing is just a Mobius mapping, right? And then this complex conjugate is just reflecting through the real numbers on the complex plane. Yeah? So the action of this mapping is just a Mobius mapping and then reflection. So let's actually put down more of what it is. So W of x plus x1 plus I x3 is complex conjugate of x1 plus I x3 minus this mapping here, minus this complex number like this, yeah? And then complex conjugate, yeah? And as we know, Mobius mappings send lines and circles to lines and circles, right? So we're considering the image of the unit ball in the complex plane under W, because that thing will be the image we're studying here. That's the slice through G of B1 with H, right? So the image of the solid unit ball in the complex plane will have boundary given by the boundary of the unit ball, which will be sent to a circle itself, yeah? Yeah. So the actual image will either be the inside or the outside of the circle, yeah? And it will be, so this is the complex plane. So this is our x1 and this is our x3, and we have alpha up here. Taking alpha to be positive, I think we have. So this is alpha I up here, yeah? So if we have that alpha is bigger than 1, yeah, then we are outside of the unit ball in the complex plane. Yeah? So then the image of the solid unit ball won't contain infinity, right? So it'll be a bounded thing. Yeah? Yeah? So this is the solid unit ball, so it's going to form itself. Since the boundary is either a line or a circle, the boundary of this unit ball is not touching the singularity, so it's going to form a circle. It'll be a bounded circle, which we mapped somewhere over here. Yeah? Okay, so tell me what happens as alpha tends towards 1. So as we allow alpha tends towards 1, which is the same as taking in this picture right here, where we are having this mapping and we're taking the solid unit ball, we're letting the alpha tend closer and closer to the top of the solid unit ball. Tell me what's happening in this picture. What happens to the image as alpha tends towards 1?
The ball gets bigger and bigger.
It gets bigger and bigger, and in the limit, what is it? If we actually had alpha was equal to 1, what would it be? Yeah, so in this world, we are just talking about Mobius mappings, right? So this guy here, if alpha equals 1, then the boundary of the circle actually contains the singularity of the Mobius mapping, right? So then the boundary of the circle is sent to a line, right? It's now sent to a line, not to a circle anymore, you know? And therefore the image of the interior of this circle will have to be a half plane on one side or the other of that line. Yeah. So as we let alpha tend towards 1, then indeed the circle gets bigger and bigger, and in the limit when alpha is equal to 1, we actually get a half plane. And in our circumstance where we're considering this thing, we can let A be equal to 1, which is equivalent to alpha be equal to 1. Let me say that again. We can let A be equal to E3, which is equivalent to alpha be equal to 1, because we would still have on the open ball of radius 1, we'd still have a diffeomorphism if we put the singularity on the boundary of the solid ball. Yeah? So in that case, what this thing would be a half plane. Right? Let me say that better. It'll be a half space. It'll be a solid three-dimensional half space. Yeah? Are you all with me here?
But this was the map representing the slice.
Yep.
Right.
Yep.
So the half space, when you have to take into account
rotations.
the rotation of it.
Yep. That's this part.
Okay.
Yeah. So let's recap the steps. So we took this part of the Mobius map, the reflection to the surface of the sphere, right? We have a solid sphere in 3 dimensions. We have A's directly on the E3 axis, yeah? And then we say, okay, let's slice it with the x1 z plane, yeah? Because we know that the image of this thing is rotationally invariant as we rotate around the xy coordinates. So if we take this slice like this, whatever shape we have, we just need to rotate it around to see what we get, yeah? And in the case when alpha is strictly bigger than 1, then the shape we get from the slice will be some large circle, or some circle, potentially quite large, which is rotated around, gives us a solid ball. Yeah? In the case when A is equal to just E3, and therefore alpha is equal to 1, then the image of the unit ball in this complex plane is a half space, a half plane, and then rotate that around, we get a solid 3-dimensional plane. Yeah? Cool. So putting these things together, what we learn is that Riemann mapping theorem is radically not true in high dimensions, that there is only 2 things we can diffeomorphically map with a conformal map, right, onto the unit ball. And that is either another ball or it's a half plane. Yeah? Yeah. So yeah, it's dramatically false in the plane. We're allowed to have any simply connected open set, which is in a massive number of things. It's an incredibly wide class of things. And in high dimensions, we just have 2 things, either a half plane or a ball. Yeah? Shows you how much more restrictive conformal mappings are in high dimensions. Cool. I'm almost out of time. Let me erase the board and state one theorem to connect this with a theme. The theme being that in higher dimensions, this theory is harder, but also some of the theorems are stronger because there are stronger restrictions for being a quasi-conformal mapping in higher dimensions. All right, maybe I should also just conclude what we've learned. So W of the unit ball is a ball or half plane in the complex plane. So G of the solid ball intersect H is a ball or half plane. Yep. So since the actual solid image like this is equal to the set of rotations of any particular slice, like this, for theta belonging to whatever, 0 to 2 pi. It's just writing in the language of maths, something I probably could have just written in words, but whatever. Again, this is this guy that's rotating the xy coordinates. 0, 0, 1, 0, 0. So G is a solid ball in R3 or a half space. And the other parts of this Mobius mapping, the reflection through a coordinate axis, E1, this mapping I call the I, the conformal matrix M, all of those things don't change the shape. So given any F conformal diffeomorphic on the unit ball is a ball or half plane or half space, i.e. Riemann mapping theorem is radically false. And quasi-regular mappings in the limit are quasi-conformal mappings. So this gives you a hint of some of the greater restrictions that might be around for quasi-regular mapping. So here's just one theorem indicating that. So theorem, suppose F, so we have to, in the most general form, we define it in W1n, because we want to have integrable derivatives. So we have f in W1n into Rn and quasi-regular regular and locally homeomorphic, locally a homeomorphism. So at each, let's not do this in a subdomain, let's take it in entire Rn. So we are doing an entire Rn. And it's locally a homeomorphism. So for every point in Rn, there is a neighborhood for which this thing is locally, in which this thing is invertible on that neighborhood. A homeomorphism. i.e. for each x belonging to Rn, there exists R bigger than 0, such that f restricted to this ball is invertible. Okay. Then f is actually a homeomorphism on the entire plane. It's globally invertible. Rn. So being locally invertible gives us that we're actually globally invertible. Is this true for holomorphic mappings? I guess from the way I say it, the answer is no. What would be a counterexample for holomorphic mappings? What would be an example of a mapping that's locally invertible at every point, but it's not globally invertible? Here's an example. So consider f of z, which is equal to e to the z, which is equal to e to the x, e to the iy. Right? What does this mapping do? If we take the strip from pi, or from minus pi to pi in the complex plane, yeah, then what happens if we consider the action of this guy? Well, if we say this is 0 right here, if we take a vertical line going down like this, right, that's going to form a circle like this in the image, yeah? And if we take a horizontal line like this, that's going to form a ray coming out like this, yeah? I'm studying this guy. But then if we consider the next strip up, then from pi to 3 pi, then it does exactly the same thing. So from what we see here, we see that we can map the entire complex plane except 0 via this, we can map this strip onto the entire complex plane except 0 itself. You know? And since the periodicity of this thing, right, if we just move up by 2 pi, then exactly the same thing is going to happen, right? So this guy maps every strip onto the entire complex plane except 0. Yeah? So it's radically not a homeomorphism. It's every point except 0 has accountably many preimages going up along a vertical line spaced apart by 2 pi. Yeah? Yeah? But locally it is a homeomorphism. It is a homeomorphism. If you take any point here, then you're totally fine. If you take a point even on the boundary here, you're still totally fine. Everything works completely well. It's locally invertible around every single point, but it is not globally invertible. Yeah? So we have different things going on for quasi-regular mappings in higher dimensions, and the kind of thing underneath that is the rigidity of conformal mappings in higher dimensions. And we'll talk a bit more about this on Wednesday, and without proofs, and then we'll just end our summary of quasi-regular mappings in Rn. Okay. Everybody happy? Any questions before we sign off? All right. See you.